Hey everyone, so we're going to get started on lesson 8, which is all about, or excuse me, unit 8, lesson 1, which is all about exponential and logarithmic functions. So we're going to start with exponential functions and looking at their graphs and the transformations of those graphs. So we've talked a little bit about graphic transformations before and how you can establish a parent function and then shift it left, right, up, or down, make it wider or steeper from there. And so same idea here. So exponential variables, the definition of your function is f of x is equal to b to the x power. So your x variable is in the exponent position. This is an exponential function with a base of b, and I apologize for the typo on your paper. We're going to change that to a b, where b has to be greater than 0, so it is a positive value. And it's not equal to 1 because 1 to any power is just 1, so that doesn't do you much good. Okay. If b is between 0 and 1, then it's going to decrease. All right. If it is greater than 1, it will increase. All right. So those are the difference in the directions of those graphs. And so you're looking at things like this where you have 2 to the x power or 10 to the x power. We're going to refer to those as exponential growth. And then anything in between 0 and 1 where your b is a fraction, you're going to have exponential decay. Okay, so this is your exponential decay. This is your exponential growth. So decay and growth. Okay, and that would be your parent function here. We'll also be dealing with e, which is a number value similar to pi. So pi, recall, is 3.14159, and it just keeps going. All right, e is also a numerical value. You can find the e button on your calculator, and even more specifically, e to the x power is often on your calculator. So you can see your E button just below the log button most of the time, right above LN. So the logs have to do with logarithm and logarithmic functions, which we'll also look at in this unit. And then E or 10 to the X, both are just related to those exponential functions. So they're inverses of logs essentially, and that's why they're next to each other on a calculator. But we're just going to look here, E to the first power, so you can see the actual value of E is 2.718281828, and that keeps going. That's rounded off by the calculator itself. So you can see that that value is greater than 1. So since E is 2.718, this is growth. It falls under that category. So it doesn't have to be a whole number to fall under the category of growth. It just has to be greater than 1. Okay. So properties of exponential functions, again, anything b to the x power, the domain is a set of all real numbers, always. All right. The range is going to be from 0 to infinity, whether it's growth or decay. We're not going to cross over the x-axis. We can't go into the negative y's. The function is increasing if b is greater than 1 and decreasing if it's a fraction. We talked about decay and growth. So increasing is growth, decreasing is decay. The y-intercept of the graph is 0, 1, because if x is 0, then b to the 0 power is 1. And so that's always true. And then the graph has an x-axis as your horizontal asymptote, so it's not going to cross through this. Now, there are exceptions to this rule because the whole premise of this lesson is transformation. Now, that doesn't mean you can't take this parent function and shift it down here by simply taking y equals b to the x minus 7. Well, that's going to shift your y-intercept so that even if this value is 1, we're still going to shift down 7 from that original y-intercept. Okay, so that's what we're going into now. Okay, so transformations on exponential functions. The previous properties can be expanded to include examples that utilize the transformations. And so this is the formula we're going to use for that. And we're going to look at, like we did before, what do the values of a, h, and k do to your graph, and how do they shift that so that you can sketch a rough graph of it or describe the transformation without even utilizing a graphing device. Okay, so when doing transformations, keep in mind here that your parent function is f of x equals 2 to the x. And so we're looking at growth going through 0, 1 and increasing up. All right, so similar to the transformations in the past, if you have f of x is equal to 2 to the x plus 1, that 1 that is grouped with your x value is going to shift this whole graph left 1. And so instead of crossing at 0, 1, it's going to actually cross at 0, 2. Right? And then that 1, 1, or 1, 0, excuse me, that we had as the y-intercept will be shifted over 1. All right, so we get this graph here. Nothing else has changed about the shape. And so our domain is still all real numbers. Our y-intercept, though, is now 0, 2. But our horizontal asymptote, and I didn't save myself much room down there, is still y equals 0. All right, it's never going to cross that 0 line. All right, when you're doing f of x is 2 to the x minus 3, and then plus 1, again, anything in the exponent position will shift it left or right. So this is going to go right 3. And then any constant on the back is going to shift it up or down. So plus is up 1. Okay, so your domain for this graph is still all real numbers. Your range is still going to go from 0 to infinity, where it's never reaching 0. And your asymptote is still going to be y equals 0. And so again, your asymptote. All right, so those, again, those relationships as before are still there. If you have an h value grouped with your x, that moves it left or right. So in this case, right 3. And then a constant in the back moves it up or down. So this will shift it up 1. And so we know that this goes through 0, 1 originally. We're going to go to the right 1, 2, 3, and then up 1. And that's where our new coordinate will be for this function. Okay, it's still going to now approach a new asymptote. So it's not going to cross the 1 at all because we're always adding 1. So even if this, as this approaches 1, it will never quite reach it. All right, so this comes like this and then goes up this way. Okay, if x is 0, then 2 to the negative 3 is 2 to the third inverted, so that's 1/8. So it'd be like 1 and 1/8. So you can see it's crossing just above the 1 there. If it is 3, which is where we have moved it, then it's 1, and 1 plus 1 is 2. Okay, if it's 4, then it's 2 plus 1, which is 3. So it's going up just 1 over 1 right there. Okay, so you can kind of just see by plugging in some of those coordinates where that will end up. The domain for this function is still all real numbers. The range, though, has now shifted up 1, so we're going from 1 to infinity. And then the asymptote has also moved up to y equals 1. Okay, and then for this last one, we have an a value. And so that does the same thing as it has done in the past as well. This is going to reflect over the x-axis. And then this particular one is also going to go down too. And so again, keep in mind your parent function. We're going to flip that over. And so here's what it looked like if it was just reflected. Oops. Over the x-axis, something like that. I got a little wide there, but we're going to then shift that down 1, 2 as well. So that as this value gets closer to sorry, gets closer to 0, it will get closer and closer to -2. And so that creates that horizontal asymptote. So we once again have a domain of all real numbers. That's not going to change on these. We have a range of negative infinity now because we've flipped it over this x-axis to -2. And we have an asymptote of y equals -2. Okay. And that pretty much sums up the graphing aspect of it. Now, you do have access to a graphing calculator. If you're not careful, these are not hard to accidentally type in incorrectly. But just being able to look at an equation and describe to me those transformations is important. So even if you can graph it in a graphing calculator, understanding the difference between your new graph and the parent function. Okay. The other thing that you see exponentials used for is compound interest. This unit is kind of cool because it does actually have a lot of real life applications in terms of something that you could use it for. Anytime you use a credit card or take out a loan or buy a car, your interest that you get on those items is often compounded. And so how it works is you put money in, interest is compounded or calculated and then added into the total amount. So you add the interest amount to your original amount, which increases that amount exponentially. And so though you may have borrowed, for example, this much, if it multiplies interest by that and then adds that back in, well, now you owe this much. And now it's multiplying interest by this new amount, adding that back in, and now you owe this much. So as it compounds the interest, it goes up exponentially. Or you could exponential decay for like the shelf life of an antibiotic or something like that. Okay, so there's two types of compounding. You can compound it several times throughout the year. So we say n times per year, or you can just continuously compound. So every time interest is calculated, it's added in, and that's just on a continual loop. They just keep doing it. Okay, so if it's continuously compounded, we're going to use this formula here that's been derived already for us. If it is compounded n times per year, then you're using this formula here. And so really it's just a matter of plugging into the formula and making sure you plug everything in correctly. Where P is your principal or your initial amount, R is your rate as a decimal. N is number of times per year, and T is time. Okay, if it's annually, then the number of times per year is 1, obviously. Semi-annually, N is 2. Monthly, it's 12. Quarterly, it's 4. Daily, N would be 365. Okay, so just using those things to set up a problem and then solve it. Again, most of it's calculator work, but knowing what to plug in and where is important. All right, and that's really it for exponential functions. Let me know if you have any questions.